Hello everyone and welcome to the last of our differentiation videos for now. We're going to be differentiating some more trig. We're going to look at tan, sec, cosec and cot specifically, and we're going to bring together all of the rules for differentiation we've learned so far in this fortnight: the chain rule, the product rule, the quotient rule, the exponentials, the logs, everything. Everything is going to be bundled in to the stuff that we're going to do today. Okay, sorry about that. Literally started recording, someone walked into the room. So what you'll find when we differentiate these trig functions is that a lot of information is given to you in the formula book, and you might be thinking, yes, a little bit of a little bit of freedom, a little bit of weight off my mind. But you do still have to understand how these basic relationship works, and there are certain rules that you are required to understand how to derive. Now, we're not getting into first principles in trigonometry just yet. We'll do that later in the term when we study small angles. But we will be deriving, first of all, tan x to show that if you differentiate tan x, you get sec squared x. And we will also be differentiating sec x to show that you get sec x tan x. Over on the left here, I've copied a section from the formula book. This is the information that you're given regarding differentiation. So you can see at the top here, you're given the first principles formula, as you already know, you've seen that. But you're also given this list of standard results. Now, the bottom one here, the bottom one is the quotient rule, which is written in terms of fx and gx. So we've got f dash x gx minus fx g dash x over g of x all squared. Now, we know that as so u prime b minus u v prime over v squared. Right? We've studied that in a slightly different way, but it is there. It's there for your reference. The product rule isn't, but the quotient rule is. Now, above this, you'll see we've got derivatives of tan, sec, cot, and cosec. And we use these a lot. Okay, so you can see here that tan of kx differentiates to give you k multiplied by sec squared of kx. So effectively, tan differentiates to sec squared. The k follows the same pattern that we've observed so far when we've differentiated sine and cos and e. Sec x, all right, differentiates to sec x tan x. And again, the k follows that pattern. Sec kx becomes k multiplied by sec kx tan kx. Cot of kx differentiates to minus k multiplied by cosec squared of kx. And cosec kx differentiates to minus k multiplied by cosec kx cot kx. Now, you will always have these, all right? You can have your yellow sheets in front of you. It's got that information in front of you in the lesson, and you will be given this in the exam. So let's get into how we use them. We've been asked here to show that d by dx of tan x equals sec squared x. Now remember, d by dx of tan x it's like an instruction. Read it like an instruction. This is saying differentiate tan x with respect to x. So how do we do that? Well, first of all, we need to remember that tan x is the same as sine x over cos x. Now, how do we differentiate a fraction where we have two different functions of x? We use the quotient rule. So let's write our quotient rule just down here. All right, we've given it down here, but we know it by a slightly different way. So we learned it as v du minus u dv all over v squared. And now we have to write down what our u and our v are. Remember, from the quotient rule, the u is the denominator, so we can say that u is sine x, and we've got that v is cosine of x, u divided by v. We differentiate u with respect to x, and we get cosine x, and we differentiate v with respect to x, and we get minus sine x. Notice you're not given these results in the formula book. These are the ones that you really have to learn and understand. Sine differentiates to cosine, and cosine differentiates to negative sine. So now we just substitute these in. So we'll say that dy by dx is going to be v times du. So v multiplied by u prime there. You can see cos x multiplied by cos x, which is cos squared x. And then we've got u multiplied by v prime. So we've got take away sine x multiplied by minus sine x. So we're going to subtract this minus sine squared x. And then we're going to divide by v squared. v is our cos squared. So now it's just a case of simplifying. Okay, cos squared x minus sine squared x is cos squared x plus sine squared x. We're going to divide that by cos squared x, that's our v squared. What's cos squared x plus sine squared x? Well, we already know that it's 1. So we have 1 over cos squared x. And 1 over cos squared x is sec squared x. And so all we had to do to differentiate tan was to use the quotient rule. And we can see that we get our sec squared x as required. Now, we're going to do exactly the same thing down here with sec x. Now we can see from the standard result, sec x differentiates to sec x tan x, and we're being asked to show that that's the case. And again, we're going to use the quotient rule, because sec x is, by definition, the reciprocal of cos x, 1 over cos x. We're going to use our quotient rule, which again I'll write out. It's always good to write out the quotient rule every time you use it. So v du minus u dv divided by v squared. This time u is 1 and v is our cos x. If you differentiate 1 with respect to x, you get 0, and if you differentiate cos x with respect to x, you get minus sine x. So let's plug all of this into our quotient rule. We get dy by dx equals v times du, so cos x multiplied by 0, that's 0, minus u times dv, so 1 multiplied by minus sine x, so we've got minus sine x, divided by v squared, so we've got cos squared x. Obviously, subtracting negative sine x is just sine x, divided by cos squared x. And the next step isn't massively intuitive, but it's a pattern that you need to be able to spot. Another interruption, sorry. And this is also a skill that you need when you're simplifying trig identities. So let's look at sine x over cos squared x. I could split this up into two fractions, the product of two fractions in fact. So sine x over cos x multiplied by 1 over cos x. Right? Makes sense. There's no reason really that we should do that, but we can, because this is, it's the same equivalent fraction, just got the product of two fractions. Sine x over cos x, we know, is tan x, and 1 over cos x is sec x. Now, the way that we tend to write this is sec x tan x, which is our standard result, sec x multiplied by tan x. Now, those two you are expected to be able to do. And in fact, you can go further. You could do cot x by doing cos x over sine x, using the quotient rule. You can do cosec x in much the same way as you can do cos x. All right, so we can actually do all of these using the quotient rule. But those are I would say, the two that we really need to know. So this all looks pretty complicated, but let's just get into it and see how we can use these standard results in the questions that we need to solve. So here we have a question. Differentiate y equals cosec 2x over x squared. Right. How do we differentiate when we have a fraction of two functions of x? We use the quotient rule. Now again, just to repeat, it's good practice to write down the quotient rule every time you use it. Then the examiner knows what you're doing, even if you mess it up, which you won't, but even if you mess it up. So v du minus u dv divided by v squared. Let's label our u's and our v's. So in this here, we've got u is cosec 2x, that's our numerator, and our v is x squared. Now, how do we differentiate cosec 2x? We use our standard result. So we look it up, we say f of x is cosec 2x, this time our k value is 2. And to differentiate it, we're literally following the pattern. So we have minus 2 cosec 2x cot 2x. Okay. Now, nothing huge about that. Let me just move this around a little bit. that is just literally applying that standard result. So I'm just moving my v so that my working's a bit more coherent. So again, just to reiterate, cosec 2x, when we differentiate it, we get minus 2 cosec 2x cot 2x, and we are just using this result down here. Okay, so differentiate v with respect to x, we get 2x. So now it's just a case of using the quotient rule. So dy by dx is v multiplied by du dx, so we have minus 2x squared cosec 2x cot 2x, just literally multiplying these two things together and putting it in a nice algebraic order, minus u times dv by dx, so we've got cosec 2x multiplied by 2x, so we've got minus 2x cosec 2x, okay, so cosec 2x multiplied by 2x, and then we divide big fraction this, x squared squared, which I'll put in, we can simplify in just a second. Now, when you're at this point, and this is kind of what I was saying with the product rule and quotient rule, you have a correct derivative here. It's done, all right? It is finished. The majority of the marks for this question come from getting this result correctly. And if you were asked to calculate a gradient, if you were asked to calculate the equation of a tangent, equation of a normal, any of those other questions that you normally are asked for differentiation, you could just directly substitute your x value in, and you will get the correct gradient. However, if you're asked to differentiate the function, you should simplify. So let's have a look at this numerator. We're looking for some highest common factors. Well, I can see that minus 2 is a common factor in both of these terms. I can see that x is a common factor in both of these terms. I can see that cosec 2x is a common factor in both of these terms. So let's put all of those as the highest common factor. So we had minus 2, we had x, and we had cosec 2x. Okay, those are the things that are common to both terms on the numerator. So then the question, what do we multiply this minus 2x cosec 2x by in order to get minus 2x squared cosec 2x cot 2x? Well, we're multiplying it by x multiplied by cot 2x. Okay, if we multiply these two terms together, we should get this term. So minus 2x squared cosec 2x cot 2. And then, what do we multiply minus 2x cosec 2x by in order to get minus 2x cosec 2x? We just multiply it by 1. Then we multiply it by plus 1, because when we do multiply this minus by this plus, it gives us the minus that we wanted. So then all we have to do is divide by the x squared squared, which would be x to the power of 4. All right, let's do a little bit of simplification then. I can see that this x on the numerator can cancel with one of my x's on the denominator. So I've got minus 2 cosec 2x multiplied by x cot 2x plus 1. And instead of x to the power of 4, I'm going to have x to the power of 3. Now, I'm not cancelling this 2x. This 2x is bundled up with the cosec, right? We can't just divide by x here, in case you're wondering. Now, that's as simple as this goes. And so we have our correct derivative fully simplified. Okay, I thought that was another interruption, but it wasn't. Now, I'm gonna delete this. Okay, so you can have a look at it. You can take a picture of it, and the lesson examples PDF has this, so you can use it to make notes from. But I'm just going to delete it so that I can work on the next question. So we have y equals sec to the power of 3x. Now this isn't a fraction. In fact, we're going to use our sec x result, but this cubed, what do we do with this cubed? Well, let's remember that sec to the power of 3x is sec x cubed. Okay, those are the same exact things. And the thing we need to do here is to apply the chain rule, because we have a function in the bracket raised to a power. So when we apply the chain rule, if you remember the shorthand method of applying the chain rule, we move the power down in front of the bracket. We drop the power by 1. Okay, so we treat the bracket like it's just anything that we differentiate. move the 3, drop the power, and then we multiply by the derivative of whatever's in the bracket. So we differentiate the bracket and multiply the two things together. Hopefully you do remember that from the chain rule. If not, then you go back and do a little bit of practice. So when we differentiate sec x, we go back to our standard results. We differentiate sec x, we get sec x tan x. Okay, there's no k value here, right? It's just 1x, so our k value is effectively 1. Let's do a bit of simplifying. We'll remember that sec x all squared is sec squared x. And if you multiply sec squared x by sec x, you get sec cubed x. So there we have our result just by using the chain rule. So again, all these examples are in the lesson examples PDF. You can obviously watch this video back to see me explain it through once more. But that's it, okay? All we've got to do now is to get into questions where we've got to find equations of tangents, etc., etc. And I'm not going to do any examples of those in this, because you'll have a look at those types of questions in the lesson, and I'll be able to help you with those. If you're working remotely, obviously, you can post your questions in Teams and I can help you. Now here's an interesting question. It's a bit similar to the chain rule when we differentiated a function that had x in terms of y, which is what we've got here. But this one's interesting, and it's a little bit separate to everything we've done. But it's interesting because, look, x equals sine y. We have to show that dy by dx is 1 over the square root of 1 minus x squared. And the big question is, where did the trig go? Why has it disappeared? Now, there's something here that I want you to look for. When you've got the square root of 1 minus x squared, it's ringing some bells for me, and I'll explain that as I go through the question. So we'll start off, we've got x equals sine y. Let's do what we did before. We'll do dx by dy, okay? If we've got x in terms of y, we differentiate x with respect to y, and we get cos y. Now that means that dy by dx is just 1 over this, the reciprocal, okay? 1 over cos y. And the temptation is to say it's sec y, okay? But I'm going to do a little bit of work over here because I'm trying to get rid of this trig somehow, right? And I'm told that I need to get rid of this trig. So I'm going to use a few tricks. Let's go over here and have a look at x equals sine y. Now, I've been asked to do something where I've got x squared. So it makes sense to me to find out what x squared would actually be. So x squared would be sine squared y. Makes sense. Now, sine squared y is also, sorry, that was an interruption again, is also 1 minus cos squared y. Right? We know that because sine squared plus cos squared is 1. And you might be able to see where I'm going with this. All right, cos squared y, we've got cos y there. So let's rearrange this and say that cos squared y is 1 minus x squared. So just rearrange this. Added cos squared y to both sides, subtracted x squared to both sides. And what that means is I can now square root both sides, and I can see that cos y is actually the square root of 1 minus x squared. Bingo. And so at this stage, I can just put that back in and say we've got 1 minus x squared. Now you have to show all that work in order to get the full marks for that question. But when I said earlier, this was ringing some bells for me. Whenever I see the square root of 1 minus x squared, because I've done these questions so many times, my brain is trained to think sine squared plus cos squared is 1. And the reason for that is because when we rearrange the sine squared plus cos squared as 1, we invariably end up with, for example, cos squared y equals 1 minus sine squared y, okay? And sine squared y is our x squared. And then to get rid of the squared, we just square root everything. So whenever I see root 1 minus x squared in a differentiation question, I'm thinking sine squared plus cos squared is 1. How can I use it? And this is what that led me to. So that's this lesson done and dusted. We have finished differentiation for now. We'll come back to do a little bit more differentiation, but in all honesty, The vast majority of differentiation in the A level has now been covered. So well done, and I'll see you in the lesson.